Our group chose the airplane on a string scenario. And first off, we drew a system schema labeling what forces and what objects were present in the scenario. In this case, that would be the airplane, the earth, and the clock. Then we moved on to the force diagram. And with the force diagram, what really helped us was actually drawing a visual picture of what exactly the scenario looked like. In this case, the airplane was attached to a string and was revolving horizontally um, in a circular path. So first, we labeled a gravitational force done by the Earth, which would be going downwards. And then we labeled the tension force, which was actually at an angle. And the reason why we said it was at an angle was specifically because it wasn't just attached vertically from the object that it was hanging from. It was really attached at an angle. Because the force was at an angle, we thought that the best way to handle that would be also to draw in the vertical and the horizontal components for that tension force. And we also decided that the vertical component force of the tension force would be equivalent to the downward gravitational force. And this was because there was no vertical motion. This helped us also decide what the net force would be. In this case, the only force that was not being equalized or neutralized by was the horizontal component tension force. And we also confirmed this using a vector addition diagram, which we found where the only thing that was remaining between the beginning and the end of our vector addition diagram was a horizontal arrow, which was exactly the magnitude of the horizontal tension component force. We also drew a motion map, and this motion map helped us to depict the circular motion of the airplane. And in this case, this is the top side bird's eye view of how the airplane was moving. And in this case, the arrows and show exactly what direction the airplane would be traveling in. And this also helped us figure out how to determine things like the radius, which would be from the center over here to the side of the circle, as well as what direction the airplane would be traveling in.
So for our measurements, the first thing that I measured was the force with the force reader right here. And ours was around 5, so I put like 4.9 since it was like almost 5. And then I used the clock tool and then the angle measuring tool here to measure the angle of the airplane at certain intervals of time. And at certain times, my intervals were not consistent because, as you can see, sometimes like here, the angle reach a maximum, or like here, and I wanted to record that. So sometimes my intervals weren't consistent. And I record these in my notebook, as you can see here. And I also use the negative angle to represent when the airplane would go to the left side.
So we decided to go with trial 1 with a force reading of 4.9 newtons. And we chose the point where the time is equal to 0.175 seconds and the angle is 53.9 degrees. And as you can see in the triangle picture below, there's the angle 53.9 degrees and the hypotenuse represents the force of 4.9 newtons. So to find the other forces, we use sine and cosine to get in a force of negative 3.96 newtons and 2.89 newtons, and we also found a gravitational force of negative 2.98 newtons. And so to find the mass, we just used the gravitational force, negative 2.98 newtons, divided by 10 to get a force of 0.298 kilograms. And to find the net force, we basically just combined all the forces. So negative 2.98 newtons plus negative 3.9 newtons plus 2.89 newtons to get a net force of negative 3.96 newtons. And then with that, we use the equation force equals mass times acceleration to find the acceleration. So negative 3.96 newtons equals 0.298 kilograms times acceleration to get an acceleration of negative 13.29 meters per second squared. And then we have to find the radius, so we combine the equations. Velocity equals 2 pi times radius over time, and acceleration equals velocity squared over the radius to get an equation of radius equals acceleration times time squared over 5 pi squared. So we used the acceleration negative 13.29 meters per second squared times 0.175 seconds over 4 pi squared to get a radius of negative 0.059 meters. And for the velocity, we use the equation net force equals mass times speed squared over the radius, so negative 3.96 newtons times 0.298 kilograms times speed squared over 0.059 meters to get a velocity of 0.89 meters per second. And those are all the calculations that we did for our lab.